So thank you all for joining us for the SZ4D International Seminar Series, and thank you for finding us at our new Pacific Rim friendly time here at 4 p.m. on Thursday. So this is the second one, and I believe the last one we're doing in this slot, and then we'll be moving back to Friday mornings Pacific time. But we are pleased today to introduce, to welcome Emma Hill, who's the Director of Research and Strategy at EOS in Singapore, and who has graciously agreed to get up extremely early in the morning to give us this talk. Emma did her PhD at UNR in 2005 and her bachelor's from Newcastle on Tyne in the UK in '99, and has been at EOS since 2010, I believe, and is really become the go-to expert on the geodesy of Sumatra. And so that's what she's going to talk to us about the geodetic and paleogeodetic studies of the Sumatran Subduction Zone. Thank you very much, and I look forward to it.
Okay, thank you so much, Emily. Thank you for inviting me, and thank you for everybody, especially everyone in the East Coast who's using their evening for this. I appreciate it. Okay, so I'm going to give you an overview of the Sumatra Subduction Zone. Let me make sure I can change slides. There we go. Okay, so to start off, just a few introductions. These are past and present members of my group, plus a few others who've all contributed to the work I'm going to present. And then I also want to acknowledge the Indonesian Institute of Sciences, who co-maintain the GPS networks with us, LIPI. So to get you oriented, I'm going to talk about the Sumatra Subduction Zone, which is subducting the Indo-Australian plate and its oblique convergence. So it's partitioned across a number of structures, and I'm going to talk about that first. I'm going to start off focusing a bit on the Wharton Basin in the Indian Ocean, and then move on to the Sunda megathrust, which, as you no doubt know, has been really busy and kept us busy for the last few decades. So before I move on to the scientific questions that I want to talk about today, just a couple of slides on our data sources. So the first one is the Sumatra GPS array, or the SUGAR, and the stations are shown here with the white dots. Some of them were installed as early as 2002, and then the network was quite a lot densified in 2010 onwards. And in case you're interested, our networks in general across South and Southeast Asia are doing okay through the pandemic. We're operating at about 70% capacity, all thanks to the help of all of our in-country collaborators who are keeping things going for us despite the border closures. And then we supplement the GPS data in terms of modern records with INSAR data where available, and with seismic data. And then the other important source of data that I'm going to be talking about today are coral paleogeodetic data. And for those of you who may not be familiar, these are a particular type of corals that we're lucky enough to have on the Four Rock Islands of Sumatra. And these grow to the low tide level at any time. So they basically act like natural tide gauges that record the vertical motions of the land over the earthquake cycle. So it's quite a few questions. I'm going to approximately talk about these. It was hard to decide what to talk about since there've been so many events at Sumatra in the last few decades. But I'm going to start off talking about the Wharton Basin and plate partitioning across the Wharton Basin, the Sunda megathrust, and the Sumatran fault, and then move on to the idea that the coral data show us that there's this fairly robust pattern of slip partitioning between great earthquakes, and what is the role of the subducting plate in defining the rupture extents, and what is the nature of these persistent barriers to rupture. I'm then going to talk a little bit about interseismic deformation, and in particular thinking about transient changes in that. And then finally, something on the shallow megathrust and how we can leverage the networks for additional applications. So starting off with this first question. So the Wharton Basin is geologically quite interesting. It previously housed the Wharton Spreading Center. So particularly noticeable features are these big, long, approximately north-south trending fracture zones that are a remnant of that spreading center. And then there's also sporadic seamounts and other features. And we've long known that the Wharton Basin wasn't completely stable, but that rather it's been a zone of diffuse deformation. And by the way, the QR codes are for the publications if you're interested in looking anything up more. And this idea of diffuse deformation was really solidified with the magnitude 8.6 Wharton Basin earthquake sequence, which was a collection of strike-slip events on conjugate faults. And importantly, the geodetic and the seismic data showed that those ruptures were deep. They probably went into the oceanic mantle. There's certainly some conversation going on between the Wharton Basin and the Sunda megathrust. So this figure here shows the seismicity in the Wharton Basin with the time that everything starts up being 2004, the time of the Aceh Andaman earthquake on the Sunda megathrust. And you can also look at this figure here, which shows the co-seismic offsets for the 2012 Wharton Basin earthquake. And it doesn't take much imagination to see that this must have impacted the stress field of the forearc as well. And you can see that also from the post-seismic displacements as well, and from stress modeling. So this idea of the conjugate faulting was initially, the fracture zones are obvious. The conjugate faults were required by the seismic and the geodetic data. But then Satish Singh and crew went out after the earthquake and did some high resolution bathymetry and seismic reflection surveys and corroborated this idea, showing that indeed there were offsets, that there's active both north-south and east-west trending faults. And this and previous ideas contributed to this idea that big earthquake and this diffuse deformation is potentially part of us seeing the nascent formation of a plate boundary. And this comes about basically because the Indian plate is hitting continental collision to the north. So it's relatively slower than the Australian plate, which is hitting subduction at the Java and Sunda megathrusts, which is easier to accommodate. So you have this gradient of displacement across the Wharton Basin. Those two plates don't want to be one plate, and they're trying to split apart along that area. And these seismic reflection results also highlighted the relatively recent initiation of these old fracture zones towards this idea of a plate boundary. Another thing that earthquake sparked people to think about, and in particular Kyle Bradley for this paper, was to what extent is the Wharton Basin actually accommodating some of the oblique plate convergence experienced at Sumatra? And so on the left side, you have the more traditional view, which was that there was a rigid oceanic plate and then a stretching forearc and the rest of the oblique accommodation on the Sumatran fault. And this was corroborated at the time by the idea that slip rates on the Sumatran fault, based on geological offsets, went from relatively low in the south to quite high in the north. So that was the reason for this evidence of this stretching forearc. Kyle revised several things. First, he revisited a lot of those slip rates, redid some of the dating, and established that basically the slip rates along the Sumatran fault are pretty similar all the way along at about 15, 16 millimeters per year on average. And he did a block model using those new revised slip rates on the Sumatran fault, the interseismic rates from the Sugar, and earthquake slip vectors to constrain the sense of slip. And what he established from this was actually the oblique convergence is being taken up partly in the Wharton Basin and on the Sumatran fault, and the forearc sliver acts as a relatively rigid block. And that has implications also for there were some ideas in the past that some of the splay faults behind the islands might actually be accommodating some of the strike slip motion, but there's really not much slip budget for those. The Sumatran fault zone, which runs up mainland Sumatra, is very analogous to the San Andreas, also lit up a little bit after 2004. And if you're interested in this fault, then Reno in this paper has cataloged using the GPS and INSAR data all the recent events on the Sumatran fault. And one of the things he shows is that the earthquake ruptures on this fault are very much bounded by structural features, either stepovers in the fault or volcanoes. There's some evidence for creep on the very northern part of the Sumatran fault in the Aceh segment, and you can hopefully see it here in the INSAR data. And Shengji Wei's group are actually trying to do seismic surveys on that section now to learn more about this. They started them before the pandemic. Of course, they're now on hold, but hopefully they'll get results when the borders open again. And Reno's looking some more at the INSAR results using more recent data. A question is, was this sort of accelerated by megathrust events, or is this a more permanent feature? Okay, so now on to this next question of persistent barriers to rupture and how are they defined? So still focusing on the Wharton Basin, this is a figure from Jensen Jacobs' paper showing plate ages. And you can see, because of the fact that this area housed a spreading ridge, they're very variable plate ages. And as you go across these big north-south trending fracture zones, you're going to see big jumps in plate age and therefore in plate thickness and in plate buoyancy. And this is important to remember because these features are being subducted at the Cinder megathrust. And those can be translated. This figure, it's a little tricky to look at, and just to orient your eyes, the land is light gray, which is backwards in my mind, so I struggle with it. But you've got Sumatra here. This is a zoomed in image of plate spreading rates. It's basically the spatial derivative of the previous figure. And you can see, again, there are some big variations in this region in the rate at which the oceanic crust was formed. And in northern Sumatra, they're reasonably fast spreading rates, while mid Sumatra is subducting plate that was created more slowly. And those fast rates would lead to smoother crust. Of course, it's covered by sediment, but there are differences in this as well. So moving on to the Cinder megathrust, it's been really active in the last, since 2004. It's subducting all of these big oceanic plate features. And here's a figure showing the large coseismic slip distributions since 2004. And the Sugar networks recorded 40 earthquakes in total in this time. It's a lot. That's how many were large enough to be recorded geodetically. And these two papers give catalogs of the offsets from those earthquakes. And moving from the north, this whole sequence started off with the 2004 Great Aceh Andaman earthquake. Then it skipped a little south to the 2005 Nia Simeulue earthquake. And then it jumped across the northern part of what we call the Mentawai patch, or the Mentawai seismic gap, producing the 2007 Bengkulu earthquake to the south. And then there were various magnitude 7.2, this little guy here, and then 7.8, this one here in the Banyaks, and this one here in Mentawai, which I'll talk about in a little while. So the coral data allow us to extend the records back over multiple earthquake cycles. So they give us, importantly, recurrence interval. We know that the recurrence interval in the southern part is around 200 years, and then it extends to about 500 years towards the north. And these coral data allow us to get an idea of what the rupture patches for past earthquakes were like. And this figure is from a review paper by Bell and Aaron. And what they did was look for evidence around the world. They catalog all global subduction zones, looking for evidence of persistent barriers to rupture. And this is the figure for Sumatra. And what you should be looking at here are the orange lines. And these are places where, based on the coral data, great ruptures terminate, and they don't tend to extend across those barriers. So we've got one at Simeulue, one at the Banyaks, and then one further to the south. And here's an example of how that looks with the most recent earthquakes. So the Simeulue saddle that I'm highlighting here was the southern termination of the 2004 earthquake and the northern termination of the 2005 earthquake. And that is also the location that the 96° east fracture zone is subducting under Sumatra. The 2005 earthquake reasonably robustly had this dual-lobed slip distribution with these two different patches. And the low slip patch in the middle corresponds to the subduction of the 97° east fracture zone at the Banyaks. And then at the south, the investigator fracture zone is the approximate southern termination. And that's not just one fracture zone, it's about 4 parallel ridges on the seafloor. This figure is to give you an idea of the similarity of earthquakes from cycle to cycle at this area. So the outside circles are the coral uplifts recorded for the 1861 earthquake, which was likely 8.5 magnitude approximately. And then in the small circles are the coral uplifts recorded for the 2005 earthquake. And the point that I want to make here is just that they're very similar, and these are what give the evidence to these ruptures being reasonably similar from cycle to cycle. And the 1422 data is a little more sparse, but it also suggests some pretty strong similarity between these events. We know that these subducting features are not quiet, and this figure is a result of OBS surveys, and you can see this streak of seismicity up through here that's highlighting the investigator fracture zone. And we wanted to look a little bit more at what the geodetic data could tell us about what's happening at these features. So here's an example for the Simeulue saddle. So this is the location, the southern termination of 2004 and the northern termination of 2005. And the Simeulue saddle, it's located at a kind of broad morphological high in the subducting megathrust that corresponds to that fracture zone. And it's the host to moderate earthquakes in the patch in between. And in this paper, what Paul did was look at GPS and INSAR data. He has this really cute interferogram for the 2008 earthquake, and shows that these moderate earthquakes at that patch are relatively similar and right on the morphological high. The low slip patch in the middle is quite interesting. And what we see in general is that there's really variable slip at these subducting features. The middle of that patch was actually filled in by the 2010 7.8 earthquake that happened right in the middle of that patch. Up dip of it experienced rapid after slip. So some of the slip was taken up by that, and this is a figure from Chu Chang's paper. And then down the dip of it, interestingly, was the location of this very, very long 15-year slow slip event that occurred prior to this earthquake sequence starting up. So that's a nice segue onto the next set of questions, which is interseismic deformation constant over time? And in particular, does Sumatra generate slow slip events? So this is the evidence for the long slow slip event. And what you're looking at here are, on the left side, they're the coral displacements for a period of time before the 2005 event, but it looks like the period before 1966 was likely similar. So this is representative of a typical interseismic period for the coral data. And as expected, they're subsiding more as you get closer to the trench. What you see on the right panel are the coral observations for the period 1966 to 1981. And they just spontaneously decided to start uplifting instead of subsiding. And Louisa tested all kinds of ways of trying to achieve that and looked at the probability that this was some kind of oceanic signal, but ultimately decided that the simplest way to model that is by having a 15-year long slow slip event at that location. And that slow slip event agrees reasonably well in terms of moment duration scaling, being the red dot right up at the top part of this graph. This wasn't by any means the only time that we see changes in the coral records, and Aaron's cataloged them in his QSR paper. And so here's another example, and they'll be, by the way, this you have to flip your eyes because this is plotted as relative sea level, not as land height change. So to get land height change, you need to reverse this graph. And what the corals do, that they're just plugging along at one subsidence rate for decades, and then they spontaneously change and start going at a different rate for some more decades. And there's no record of there having been a distant earthquake or something that could mean that this is post-seismic. They've already tried to remove oceanic effects. So there are some rate changes due to things like the Indian Ocean dipole, but they basically spontaneously start moving at a different rate. And initially, the way that we thought about this was to think maybe this was due to changes in the amount of coupling or changes in the down dip limit of coupling. And this is an example from Louisa, where there's 3 sets of coral rates for the island of Simeulue, where you can see quite dramatic changes. And interesting to note, the 2 right-hand ones are just before great earthquakes. The left-hand one is not. And so she modeled it like that, but the trouble with that, I guess we were a little naive at the time, and we didn't think that carefully about slip gradients. And in fact, in this figure, you have this it's a very simple model. We were using simple models because there's not much data, but you get this very dramatic change from fully locked to creeping that couldn't actually physically happen. You have to have a gradient. And so in this next slide, Rishabh revisited this and decided you actually can't get those changes by changing the down dip limit of coupling without things being a bit unphysical. So he proposes instead that you can also fit those changes quite well by assuming a very shallow slow slip event instead. And his paper will be out in a few weeks, and he discusses some interesting thoughts on how the stability and instability of the shallow megathrust could be the result of changes in fluids at that location. In terms of shorter term slow slip events, we haven't really found any. These figures show the sugar data, and Luja removed all known post-seismic tectonic signals and also ocean loading, everything we knew about, she removed from these figures. And you can see that what's left is really pretty flat, and there's no clear evidence of slow slip events. That doesn't mean that we don't have any. Even though we have quite a lot of stations there, this is a big area, they're relatively sparse. And this figure shows the minimum magnitude of slow slip event that we would be able to record using the sugar network. And it's at about magnitude 6 or so. So anything smaller than that, we're not seeing. Anything in the Engano area is difficult to pick up because there's no Four-Arc Islands, so it's difficult to see. And also, if there was another really long slow slip event happening, we're only now getting to the kind of multi-decadal time series that we would be able to pick that up. And of course, our time series are full of many other things too. Okay, so now moving on to the shallow megathrust. The Sumatra subduction zone has generated in memory at least several shallow tsunami earthquakes. So earthquakes that are shallow and generate tsunami that are larger than would be expected based on their seismic magnitude. And this figure is for the 1907 Nias Simulu region. And this was a fortuitous for the people of today, in that this earthquake caused so much devastation. The tsunami caused so much devastation on Simulu that the people from Simulu remembered this. That story was still being told, and so in 2004, the people of Simulu spontaneously evacuated, and there were very few casualties on Simulu, while everywhere else sadly did experience them. And what Stacey did for this was he trawled through historical records and newspapers. There's a lot of Dutch records from that time, and came up with estimates of tsunami inundation based on that earthquake. And then they used those to model an updated slip model, with the up-dip slip being again at this location of this subducting fracture zone. Moving now south to the Mentawai region, and I would note here is not telling this story of these kind of tidy earthquake ruptures with persistent barriers, but for this earthquake cycle at least, the Mentawai patch is breaking in a piecemeal fashion. There's coral data to suggest that it did host much larger earthquakes in the past, but in this case, we still have this remaining patch. The 2008 earthquake was quite surprising because it was a 7.2 kind of right in an area that's fully locked and waiting to go and overdue, but it didn't cascade into a big rupture. And this area produced this shallow tsunami earthquake in 2010. And that event was really shallow. It probably ruptured the top 6 kilometers or so of the megathrust based on geodetic, seismological, and ocean buoy data. It created a really devastating tsunami. It killed about 500 people, and part of the reason for the high death toll was that there was this very long period, not strong shaking. It went on for a long time, but it wasn't enough to cause people to evacuate from the coastlines. And when that happened, a lot of us were still kind of the mindset that it was a little bit surprising. And we'd been looking at these coupling models that often mark the shallow megathrust as creeping, and that's really because there's no resolution from the land-based stations of that shallow megathrust, but we'd sort of justified it, saying, well, it's shallow, weak sediments, it's clays, it makes sense that it's creeping. But this is a paper of Eric's that will be out in a few weeks. And what Eric's done here is create a new way of doing inversions where we incorporate stress constraints into the kinematic inversions. And they forbid slipping above a frictionally locked patch. It makes intuitive sense that if you're locking something down below, then it can't, there's no stress transfer, it can't be creeping shallower up. And so based on this work, we would expect that most of the Sunda megathrust is not creeping. It doesn't really matter what the frictional properties of the shallow megathrust. It could be velocity strengthening, but it can't creep because there's not this stress transfer to the shallow part. So it's not necessarily a big surprise that the 2010 earthquake happened. This area, we can continue to think about how it can initiate earthquakes and if it can initiate earthquakes, but it seems certainly capable of hosting earthquakes that are started a little further down dip, as was likely in this earthquake. So after the 2010 earthquake, they took out, Satish Singh and team took out, went out and did a seismic reflection and bathymetry survey of that area. And what you're looking at here in the top figure, the most distant block is the area that generated the 2010 earthquake. And in the bottom figure, it's the far right subregion 3 that generated the 2010 earthquake. And an interesting thing to note from this figure is that there's variation along the length of the megathrust about which direction these little shallow faults are pointing on the upper plate. And so in some areas like this one, they're pointing landward. In some areas, this is right at the toe of the megathrust. In some areas like this one, they're pointing seaward. And in the location that generated the Mentawai earthquake, they are divergent. They point in both directions. And in his paper, Kyle hypothesizes that these areas with divergent faults are indicative of a geological situation that would suggest low friction on the fault. And so a question he asks is, will imaging the fault and identifying these types of locations help us to forecast which areas would be most likely to generate these shallow tsunami earthquakes? The 2010 earthquake generated significant afterslip. And it was a little bit difficult to model this because it was still shallow. And for the co-seismic, we at least had the high rate GPS, we had the tsunami to guide us in the location and magnitude of slip. Whereas for the afterslip, all we've got is the GPS data. So Luja approached this with a rate and state friction approach. She just tried to do a forward model based on the physics. And the interesting thing that she found for this, and I should note before I go on, actually, for completeness, the 2010 earthquake would have been loaded by the down dip 2007 earthquake. So the region that generated that earthquake was already stress loaded from down dip. And then in terms of the afterslip, what Luja found was that she couldn't fit the data very well using a really simple rate and state model, but she could fit the data really quite surprisingly well if she assumed different pre-stress conditions before the earthquake to the north and south of this red line. And so essentially it kind of created this nice experiment where you could cut that rupture in half, and half of it experienced a great earthquake down dip, and the other half is up dip of a fully locked patch that hasn't ruptured in several hundred years. And so the afterslip essentially was sensitive to the pre-stress conditions on the fault. So this is what the data in the colored ones and the model in the dotted lines look like when you don't include those variable pre-stress conditions. And then this figure with the solid lines show the improvement in fit if you consider the impact of that past earthquake, which is quite interesting, this idea that afterslip can image pre-stress conditions. I haven't really talked much at all about post-seismic because that would be a whole nother talk, but I just wanted to kind of, for completeness, show this figure from Chu Chang where he modeled the viscoelastic deformation from all of these large earthquakes using these straining blocks. And there's a couple of important takeaways from that. One is that Sumatra indicates a transient viscosity for the mantle wedge. So the viscosities are variable depending on these earthquakes. And then the second thing to note is that the viscosity is quite spatially heterogeneous. For example, up in the northern part, as you get closer to Thailand, there's lower viscosities. And who knows really, but you could argue that they're related to back arc spreading in the Andaman Sea. Okay, so the final section, I wanted to talk a little bit about additional applications. And to motivate this, I thought, since this is SZ4D, it's important if anyone's considering installing new instrumentation to think carefully about the other ways, in particular for GPS in this situation, other ways that these data can be used. The GPS data, we've been talking about the traditional positioning techniques to model tectonic deformation, but there's a whole host of other things we can do with it too. So the signals measure electron density in the ionosphere. So you can look at ionospheric tsunami, which I'll talk about, and space weather. You can estimate the amount of water vapor in the troposphere. So these are really long-term climate monitoring devices too. And then once you get down to the ground, if you put your station in the right place, you can use the reflected multipath signals. So the positioning, ideally you do it all with the direct path signal from the satellite, but there's also a lot of bounced signals off the surfaces surrounding the antenna. And we can probe the properties of that reflected surface. If it's a station near the coast and the signals bounce off of the sea surface, you can actually get sea surface height from those observations. So you get land height change from the positioning, and you get sea surface height from the reflected signals. And it's way better than a tide gauge because you separate those signals instead of them being measured together. And you can get at snow depth, you can get at vegetation moisture, you can get at soil moisture. It's important to leverage. It's also useful, I would say, for getting funding. In our case, we're putting some stations out around the South China Sea, and the funding is for sea level. It's for understanding sea level processes in the South China Sea, but it will be very useful for also establishing the Sunda block, which is not a very exciting thing to write a proposal about, perhaps, but we can leverage it. So a few examples. Sumatra provided quite a nice experiment for thinking about ionospheric tsunami. And in particular, the question we wanted to ask was, would ionospheric information have helped early warning systems determine that the 2010 Mentawai earthquake was a really dangerous, shallow tsunami earthquake? And so Sumatra produced these two same magnitude, 7.8, same year, so the same observing network earthquakes. But the Banyak's earthquake, in contrast, was deep, and it didn't produce, relatively deep, and it didn't produce a big tsunami. So we asked what was the difference in the ionospheric response to these earthquakes. So what you see in the top panel is the ionospheric electron density changes for the Mentawai earthquake, and the bottom one is for the Banyak's earthquake. And you can see both in the time series, and note that the y-axis is different for those two. You can see that there was a significant response for Mentawai, and there was basically no response above the noise for the Banyak's. And you can see that also in the color plots, which show this in the frequency domain. And this can be potentially useful for tsunami warning. And I guess just to give background in case you haven't thought about these things. So you generate an ocean tsunami by lifting up the seafloor, and then you lift up the water column, and that has to move. But you also lift up the whole atmospheric column above that too. All the mass in the atmosphere gets lifted up. And so in the ionosphere, you generate a tsunami in these charged electrons in the ionosphere. And what we see from Fabio's results are that the ionospheric tsunami is picked up by our networks after about 8 minutes, which is quite a lot sooner than, 10, 20 minutes sooner than the ocean tsunami hit the land, because the ionospheric tsunami doesn't hit shallow coastlines and slow down. It keeps traveling at the same velocity. Another example of how we've been using the sugar data for non-tectonic applications is for climate. And so what you're looking at in this figure, the red time series are the first principal component of the tropospheric water vapor time series for the Sumatra state, for the sugar stations for a year. And then what you see in the blue line is the Indian monsoon index, lagged by a little time because Sumatra is a bit further south. And so these are, I hope, showing quite nicely that there's a lot we can learn about monsoon dynamics, long-term climate change, and so on, using these networks as well. And then finally, here's an example for a sea level study, and it's not a Sumatra example. And the reason that it's not a Sumatra example is because when the Sumatra stations went out, none of us were thinking about this innovative new way of probing the reflected signals of the data. And so even though there's a lot of stations that are really, really close to the coast, none of them are close enough. And so if we could redo everything, there's a lot of stations that we might move by 10, 20 meters, and we could use them for sea level studies as well. So I appeal to anyone thinking about GPS installations to think about sea level studies as well. But in this example, the green dots show the sea level changes as recorded by the GPS station based on the reflections. And then the red line is the tide gauge data. And this is for a storm surge that approached Hong Kong back in 2018. And it's kind of interesting too, like a tide gauge only measures 1 point, but for the GPS, you're picking up all the reflected signals over a swath. So you're kind of imaging a wider area, and you can get quite far out to the coast if the GPS station is installed high enough. So it has potential for looking at tsunami too. And the station can be high so it doesn't get destroyed. Then for my very final slide, I just wanted to say one thing from the social science perspective. So EOS had a team of social scientists and anthropologists working in Sumatra, and the goal of their work was to look at whether the large amounts of aid money that flowed into Sumatra after 2004 had actually helped people in the communities there live more safely in the face of disasters. And the results are a little depressing, unfortunately, because the main takeaway from the results is that these disasters and the aid that followed have resulted in much higher levels of economic segregation in the communities of Sumatra than existed prior to the in this case 2004 tsunami. And so the top figure is showing various measures of land value, and for each panel, the left one is pre-tsunami, and then the right one is today. And so what you can see is, and then the pink is the tsunami inundation area, and the blue is inland. So what you can see is that prior to the tsunami, inland and tsunami affected areas were maybe a little different, but not much. And then after, there was a significant difference in the value of land inland versus in the tsunami affected areas. And then what you see in this bottom plot are the poverty rate estimates for before the tsunami and then after reconstruction. And you see again that the poverty rates escalated specifically in the tsunami affected area. And basically what happened was that a lot of the aid agencies went in with a mandate to build X number of houses, and they wanted to do it quickly. And so they built back in the tsunami inundation area, right in the area that had been destroyed, because they didn't have the time or inclination to deal with land rights issues. But nobody wanted to live in the tsunami inundation area. A lot of people are suffering from post-traumatic stress. They understand that this isn't a good place to live. So everybody wanted to move inland, and the people who could afford to did, but the people who couldn't afford to had to stay living in the inundation area. So it's a lesson perhaps for how to think about post-reconstruction efforts in future. So I've covered a lot of things. I've talked about this idea of relatively persistent barriers to rupture, and the idea that the downgoing oceanic plate is much more important, I think, than we used to think. We used to think it didn't really contribute much to convergence, but actually it's accommodating quite a lot of the oblique convergence. We're now seeing that the features on that downgoing plate can tell us a lot about rupture processes. We see these changes in interseismic deformation rates that can potentially be explained by very long, slow slip events. And then the shallow megathrust is probably more dangerous than even now we're anticipating. For a final takeaway, I guess the thing I would say now is for Sumatra, we're primarily using the geodetic and the paleogeodetic data. We're slowly getting access through Shengji to some of the local seismic data. But if we want to really advance our understanding further, I think we need to go to the seafloor. We need seafloor geodesy, and OBS would help a lot. Local seismic data would help a lot too. Thank you.
Well, thank you, Emma. I'll clap on behalf of everyone here. I'll do the Zoom thing here. That was a great talk.
I apologize for losing my words occasionally. It's really early here.
It's terrible. It's really tough to
brain fog.
67 people out there, but you can't see any of them.
I can't see anyone, and they're all in the middle of their day.
And there are lots of questions. Before we jump to questions, I just want to correct something I said in the introduction about the series. I accidentally said that this was the last one in the Pacific Rim friendly slot, and that's not true. On May 7th, we'll be welcoming Felipe Roan from Chile, also at this slot, which is a Thursday at 4 p.m. So mark it on your calendars. Okay, let's get some questions going here. So let's start with Kellen Wang had a question. Is the peak slip in the 1907 tsunami really greater than 20 meters?
I don't know the answer to that question. Okay.
I can hear over chat a hint of skepticism in his voice.
Yeah, that's a lot. They're still dealing with just kind of historically reported data. I wasn't part of that study, so I don't know in detail the nitty-gritty of it. I agree, right. It seems like a lot. There were some models for the 2010 earthquake that had slip rate amounts of slip that high too, so I wouldn't say it's completely impossible, but I don't really know.
Okay, fair enough. Let's move on. Roland Bergman said, fantastic talk. Are there similar divergent fault systems in other areas producing shallow tsunami earthquakes? 1896 Northeast Japan, Nicaragua, Shumigan, 1946.
Another question where I don't know. I read Kyle's paper again yesterday, and I don't think he discusses that question. So it might be a question for the community if anybody else has noticed such features.
Anybody want to shout out? Unmute yourself. That's the joy of the more informal Zoom here.
I don't know about those other places with actual events, but it is ominous to note that Cascadia has shallow divergent areas in quite a range of the margin.
Great, thank you. The 1907 from Harold Tobin, the 1907 Nia-Simalu tsunami earthquake appears in the same area as the modeled up-dip slow slip event for 1966-1981. Is that right? Does it imply both modes occur on the same patch of fault? So
slides
same patch of faults, doing the lock thing and the creeping thing.
Okay. Wrong place. Try and find Reshev's slide. I would say that I don't think that the location of the 1907 tsunami earthquake is that well resolved. I keep bypassing. Okay, there we go. The shallow tsunami, the shallow slow slip event it's a little further along strike, and if you believed these, then the 1907 was kind of at the location of the 96-degree east ridge, and the slow slip event, the maximum slip was at the area of up dip of the Banyaks at the 97-degree ridge. So a little bit different, but neither well resolved because they're very sparse data in both cases.
Fair enough. Carlos Vargas says, well, first of all, comments, nice presentation, thanks. And then, have you seen thermal patterns between blocks defined by the multiple oceanic pairing areas? Do you think that the current thermal response of the lithospheric system in the area may offer relevant information about the earthquake cycle?
Can you say that again? Sorry.
Yeah, I'm having a little trouble parsing this, but have you seen thermal patterns between blocks defined by the multiple oceanic tearing areas? I think what he seems to be after is what you were saying about buoyancy and fracture zones here. Do you think that the current thermal response of the lithospheric system in the area may offer relevant information about the earthquake cycle?
I see. So just the differences in plate age will correspond to differences in temperature of that plate, and does it play a role? That's a good question. I've never thought about it. It's something perhaps people doing modeling could look at more.
Okay, I'm going to take my prerogative as a moderator here and insert one of my own questions, which I'm not expecting an answer to. But
great.
but I just want to point out something. That, you know, you made this case that you're not seeing any short-term slow slip events in the sugar network, which I'm sure came as a surprise to you, right? Because I'm sure that's part of your rationale for putting that network out there. And it's quite striking compared to similar networks elsewhere in the world. There's something different about Sumatra. And I think it seems to be a very important observation. And I also want to point out that there's something a little bit different about the Sumatran 2004 Sumatran earthquake, in that it didn't have, as far as I know, any foreshocks. Correct me if I'm wrong there.
There was an earthquake at the Engano segment in 2000, but that's pretty far away.
And it's not in 2000. Not, I mean, there's no.
Yeah, there wasn't
kind of foreshocks. I mean, it's
yeah, there was something all the way down here, but that was it, really.
Yeah, conspicuously different than the story that gets told, for instance, about the Chilean earthquakes, in particular the Iquique earthquake, or about Tohoku. So I'm wondering if you would care to make a connection between those two facts. Clearly, I would care to make such a connection. Okay, that perhaps those
Yeah, I mean,
more than one kind of margin out there, and those margins that have these short-term slow slip events also are the ones prone to foreshocks.
And I guess the one thing that we can tentatively say is that at least for the Nyasimalu earthquake, which is kind of the best documented in a way in terms of coral, we don't see foreshocks, but we potentially see big, long, slow slip events happening before them. Because that's true for 2005 and for 1861, but yeah, no actual earthquake.
Okay, and I won't dominate the conversation any longer, but moving back to the chat here, Joe Goldberg says, great talk, many thanks. Is there sufficient seismic monitoring data anywhere in the region to detect seismic activity, indication of slow slips such as tremor or repeating earthquakes? You talked very much about the geodetic story, but she's poking at the tremor or seismic story there.
Yeah, and it would be really nice to have seismic data for the islands, or ideally OBS. So BMKG, the Indonesian agency that monitors earthquakes, they do have seismic stations around on Sumatra. They've been difficult to get at, but Shengji's now working quite closely with BMKG, so I hope we'll see more. But there's been nothing out on the outer Ark Islands other than like occasional sort of short-lived campaigns, but they were picking up aftershocks so much that it would be difficult to pick out anything else. But I guess one thing I would say is if you were gonna look for slow slip events with seismic data, and you'd have to do OBS because there's only this one tiny little island called Mago in the southern part, but Enggano, the Enggano region, so the area south of 2007, has always behaved differently to the rest of the megathrust. And so the sort of from around here where my cursor is northwards, prior to 2004, the seismic record is really quiet. There's not much going on. But the Enggano segment, all the way back to the beginning of instrumental records, has reasonably high levels of background seismicity. And there's been hypothesis that it's somehow this difference is related to there's a seamount being subducted there. Our one GPS station on this island, Mago, it's the one place that we maybe see a slow slip event, but because it's only one station and it's a little bit difficult to argue with one station, we haven't made a big deal out of it. But seismic data for that area might, I think, potentially pick up some tremor.
Interesting. I accidentally skipped a question from Matthias Carvajal. Nice talk, thanks. Is there coral evidence for abrupt subsidence indicating past super shallow ruptures?
There's a paper by Belle Philibosian, which is somewhere in the Mentawai area, and she has a coral record that has an abrupt subsidence without a known seismic event, and hypothesizes that could be a shallow earthquake. It wouldn't be as shallow as 2010 because the amount of sudden subsidence is actually quite a lot larger than we saw in 2010. So it was either bigger or it was a little bit more down dip, but there's something in that. She has a paper dedicated to it, probably around 2012 kind of time.
Great.
That's the only one. I've asked the geologists quite a few times, hey, have you ever seen tsunami deposits where there was no evidence of an earthquake, and no one was really looking out for that. So they haven't really seen it, but have been thinking that would be a nice thing to go out and look for.
If you're feeling patient, I know we're over the hour, but I thought maybe we could squeeze in another question or two. What do you think?
I think Joan wanted to ask a question as well.
Joan Gomberg.
Yeah, so those was sort of two questions. One is related to Emily's question about foreshocks. Is there, what would you guess the detection capabilities are? Could there have been foreshocks that just no network
catch? That's true, yeah, because all the records of seismicity for Sumatra are based on global networks. They don't have any mainland Sumatra data included in them. So that's a good point. I don't know when the BMKG data stations were installed either. I don't know if there are any local stations prior to 2004.
But
and is there any thought or potential to add seismic instrumentation to the GPS at the GPS locations? Something.
It's a little bit of a sad story, actually. There's I don't remember exactly how many. There's maybe 6 bunkers already installed near GPS stations in the Mentawai region. But for complicated reasons, they don't have any instruments in them yet. So there's concrete bunkers ready to put an instrument in, and we can revisit that after the pandemic, I think.
yeah, and I will point out that the foreshocks of both Tohoku and Akike were globally visible. The immediate foreshocks, the days and weeks before that did not rely on. So at that level, of the similar level, there was not a similar level of foreshock activity before 2004. Got you, Bar. Okay, 2 more. Yehuda Bach. Emma, do you have interactions with the Indonesians with regard to using your data for tsunami early warning? If not, he'd like to speculate that it might help you get access to their seismic data. Or do you use real-time links to their stations?
So our data are not currently real-time. At the moment, we download every 5th day by BGAN, and it's really expensive for us to do so. For the mainland stations, it's feasible now to make them real-time, but the 4ARC stations, there's still not reliable 5G connections or anything, so it's all BGAN. But it's something on our minds, and we have a kind of 5-year plan that by 5 years from now we can try and get things real time. Maybe we can use Elon Musk's new internet everywhere constellation or something like that to get these data faster. So if we can get them real time, we will definitely provide them real time, but we don't have them yet. And we're facing more difficult funding in a few years than we have so far. So even getting the downloads that we have at the moment, we'll have to have some technological changes.
Okay, and one last question here. Tim Melbourne asks, in Cascadia, we often see small EPS-like GPS offset visible in only 2 to 3 stations with small displacements of 1 to 2 millimeters, for which we cannot really make the case that these are legit slip events. Sometimes they confirm a signal with them, sometimes not. For Sumatra, do you have access to these GPS stations from the Indonesian network, here we go again, that you might better pin down small events at the lower end of the sugar resolution?
So the Indonesian stations would certainly densify our networks. They also have some stations on the islands, and they have a lot of stations on the mainland. They're operated by BIG, which is the Geospatial Agency for Indonesia. So my recently graduated PhD student, Reno, who's from Sumatra, is working with his Indonesian colleagues on those data. They're still not available in a way that like I can work with them, but I have a new PhD student from Indonesia, and I have a graduated PhD student who are starting to work on those data. And I think those two are doing a great job of building up trust and allowing at least some analysis further to what's already been done with those data. Not yet, but hopefully soon is the short answer.
Okay, well, with that thought, I think I would normally say let's thank Emma again, but well,